exoplanet group under the supervision of Manuel Berger and Guillermo Grada. And today I'm going to give an overview of my PhD project on trying to improve the detectability of exoplanets using the radial velocity method. Probably, as you all know, the radial velocity method consists on detecting and characterizing exoplanets by studying the Doppler shift that the exoplanet induces on the stellar host spectral lines, as we can see in this animation. This was the method that was used to detect the first ever exoplanet around a main sequence star in 1995. And as we can see, it has contributed to the characterization of over 729 exoplanets over the years. However, as we can see in this plot on the velocity semi-amplitude of the exoplanet detected across the different discovery years, we see that we have not detected any Earth twin, which would induce just an 8 centimeter per second signal. And also we can see that despite the instrumental advancements, the limit at around 1 meter per second, there are very few exoplanets detected below this limit. So why is this? Why is this happen? Like, is it because is it technically difficult to measure this 1 meter per second level? Like, obviously, if we would use just one single spectral line, then it would be unfeasible to do that. However, we use the cross-correlation function, which tries to cross-correlate the spectra with a binary mask. So we boost up the signal-to-noise of our observations. So we get sort of an average line measurement by co-adding these thousands of spectral lines that we have in our spectrum. So from there, so by measuring the radial velocity on the cross-correlation function, we can measure light signals at the 10 centimeter per second precision for the brightest stars observed with the best high-resolution spectrograph like espresso. So it's not rather a technical problem, but a physical one. So the spectra or the cross-correlation function is sensitive to Doppler shifts induced by planets, but also it's affected by line shifts and light shape distortions induced by spots and faculae that enhance or inhibit some flux from some region of the star, and this induces apparent line shifts on our spectra, but also changes on the line depth and width and asymmetry. So at the end, we have a noise floor on our observations of several meters per second, which mimics what a true planetary shift would induce in our spectra. And this is happening even for not so active stars like the Sun, as we can see in this image of the Sun from 3 months ago, where we can see a dove-looking dark spot feature that it suppresses the flux from this region of the star, and it can induce changes of several meters per second. So in order to tackle this, we have developed a novel method to separate line shifts from line shape distortions in the cross-correlation function. So if we have some cross-correlation function which is affected by Doppler shifts, but also by stellar activity, we can decompose it to first order the line shift contribution by the first order derivative of the CCF. And this line shift contribution, as we said before, it will have a degeneracy between the effect by stellar activity, but also it will have a contribution from true Doppler shifts. And however, line shape distortions will induce more complex dependencies. We will try to model with this line shape distortion basis function. And the other constraint that we impose is that this line shape distortion basis function is orthonormal to these first order derivatives. So we are able to fully separate between line shifts and line shape distortions. So we have found that an optimal choice of this basis function is the Hermite basis function, which is the same as doing the derivatives of the Gaussian fit to the CCF. So by using this Hermite basis function and projecting our observations into this function, then we get a set of line shape distortion coefficients time series that measure depth changes on the CCF, width changes, or in general, asymmetry shape changes in the CCF. With this information can be used to try to break the degeneracy between this effect from stellar activity on this apparent line shift that stellar activity induces. So in order to break this degeneracy, we will study the statistical and physical properties of how we relate these width and asymmetry changes to this contribution on the radial velocity using a neural network. So due to time constraints, I cannot really go into much details of how all this works, but just that we have designed a convolutional attention network, which combines convolutional layers with multi-head attentions in the transformer encoder block. So we are able to model how stellar activity behaves on the time dimension. So as an input, we introduce these different distortion time series coefficients. And then after processing these time series coefficients with this convolutional attention network, we have a prediction on the effect from stellar activity on this line shift component. So in our observations, this is what we want to predict. So we don't have this ground truth in our observation. And this is a supervised learning method. So we need some inputs, but also some outputs of what is the true effect from stellar activity. So in order to train our network, we use StarSim, which is a stellar physics simulator developed by the group, where we can generate hundreds of thousands of CCFs, where we know that we have injected some dark spots and bright family in this stellar surface, and we know which are the distortions that introduces on the CCF. And so we know that the radial velocity that we measure from this synthetic data set is only affected by activity. So with that, we can introduce these inputs and outputs into our neural network and train it. So here I show the performance of our neural network, which we name as CANSTAR, which is Convolutional Attention Network for Stellar Activity Removal. And we compare the performance to a FCN, which is a fully connected network, which is a simpler baseline network where it doesn't use time information. And we also compare the performance as a function of the signal to noise of our observations. And we can see that our CANSTAR network is able to, and here I show the performance, so how we are able to reduce the stellar activity contribution to our radial velocity. So if we use like up to 7 or 8 coefficients of these distortion coefficients time series, we are able to reduce the RMS below the meter per second level to just a few centimeters per second. But obviously, it also matters like the signal to noise of our observations and the performance. But CANSTAR outperforms a simpler network where we don't use time information. And finally, here I show you so once we have trained our network, we apply this trained network on our observations, and we apply it to Epsilon Eridani, which is a very bright star, which is very active, and where we show that in the observations are completely dominated by the rotation period of the star and its first harmonic. And then we also overplot the CANSTAR prediction, and we can see that it's able to predict like this sort of variability in the observations. And after we remove this prediction on our observations, we get some residuals where we reduce the RMS of this time series by a factor of 2. And in the residual, we see a tentative signal at 6.09 days, but we see that it's quite close to the first harmonic of the rotation period. So we are a bit uncertain on the nature of this signal. And finally, we also apply this network to another star, where in this one, there is a known Saturn mass exoplanet, which induces this eccentric Keplerian orbit. So here we prove that our network is able to fully distinguish between what is a true Doppler shift from a stellar activity. And finally, here I leave you with the conclusions and also some of the future work that we are exploring, such as applying this coefficient computation for cross-correlation functions computed with different stellar mass, so they are sensitive to different phenomena. And also maybe instead of only producing predictions on the radial velocity from activity, also maybe we could predict what is the actual active feature map that is producing this sort of variability, just like the images of the sun that I showed you before. Thank you for your attention.
Any questions for Tony? 2 minutes blank. Yes.
So I have a question about the mask that you use in relation function. So you said it's binary mask. Do you only use the position of the lines, or do you actually also take into account the line strength? Because I guess there's more information to that, right?
Yes.
Do you use that information, or do you just?
Well, in fact, it's a weight binary mask. So we weight them according to the velocity content of these lines. So for the lines that are steeper, like they are deeper and they have like a steeper derivative, they have more information content. So we tend to weight those higher than other ones that are shallower and the radial velocity information is
Okay, so you include information for line strength.
Yes. And we would be interested also to, like, now we are selecting like a single mass from that is general for any stellar type, but maybe we would be also interested in maybe trying to see mass that are sensitive to different phenomena. So maybe using the sun and also simulations try to compare different masses and see what are the outcomes.
More questions for Charlie? No? Okay. Then the next speaker will be Alejandro. Good. Yes.
Hi, I'm Andres de los Santos, and I'll be talking about the project I'm working on, which is the impact of mergers on AGN activity across mass scales. So first thing we need to know is what is an AGN. For those who don't know, it's an active galactic nucleus, which is basically this phenomenon where the central supermassive black hole of a galaxy starts to accumulate a lot of matter, which compresses, gets super hot, and emits some insanely bright radiation that sometimes outshines the whole galaxy. So that is an AGN. And what is a galaxy merger? As the name already strongly suggests, is the process in which two galaxies, let's say, collide, and after a long, long time, they become one unit system. So a summary of the project that I'm working on is that the main goal is to understand the AGN merger relation at different mass scales. And a secondary but equally important goal is that we can put constraints on black hole growth using this relation. And hence, we can put constraints on the origins of black holes. So by the mass scale, what I'm referring to is the massive galaxy regime, in which there's plenty of literature already, the dwarf galaxy regime, in which there are only a few papers, including one that we put out earlier this year, this one. And in the white mice range, there are also a few more papers, but none of these are as detailed as the one I'm working on that I'll be explaining. So the one we already put out earlier this year, I'll refer to it as the manga paper. Basically, we took the AGN sample from an already existing paper by Mezcua and Dominguez Sanchez, 2024, and they used the BPT diagnostics to determine if something is an AGN or not. And then I went through all 3,000 dwarf galaxies from that sample and classified them by visual inspection on 6 different stages, where stage 0 is a non-interacting normal galaxy, stage 1 is a close pair, and then we go on until stage 5, which is like the last remaining of a merger. So what we found in all of these, mind you, is for dwarf galaxies. What we found is that, yes, there seems to be a correlation and an increase in the AGN fraction as the merger progresses. And this increase becomes quite noticeably after the first pass of the merger process, which happens between stages 1 and 2. But when we flip things around and we see what is the interaction fraction of the AGN versus non-AGN samples, although there is still a statistically significant correlation or difference, should I say, most importantly is that over 91% of AGN are not related to mergers or any sort of interaction. So to sum up these results, you would say that, yes, dwarf galaxy mergers can increase the AGN activity, but they are definitely not the main channel for AGN triggering. We also investigated the environment of these dwarf galaxies and found that less dense environments seem to favor the presence of AGN. So what I'm working on now, currently, still work in progress, of course, is expanding this project to DESI, where we have much larger volumes of data. Right now, the CTR1, we're talking about 18 million objects. So visual inspection is not feasible, versus 3,000, of course. So the way we're doing this for DESI is the agent selection is already done. It's available in the Galaxy value-added catalog by Stephanie Junot. And right now, I am working on step 2, which is identify the merger stages, but in an automatic way, no longer visual inspection. And then the next step is to account for all other factors that we can, which we can now do with this large amount of data. So the way of identifying mergers, classically, you would take a certain metric, such as the symmetry, which is the most popular one, and just take it and define a threshold above which you have a merger or a non-merger if it's below. Nowadays, it is much more common to use machine learning techniques, all of them, and in different ways. So you could ask, what are we adding if this has already been done? Well, the 2 key aspects is first, image cleaning. Most works do not take this into account, if not all of them. And this is crucial to get the right metrics from the image. Not cleaning results in really bad information. But also, we are not just determining if either a galaxy is or not a merger, but in which stage of the merger sequence it is. That's why I spoke about being in more detail in this work. So this is a quick example of why cleaning an image matters. Here you have a galaxy with a smaller galaxy that's the contaminant in the image because it's overimposed, but it's not on the same plane. And as you see, this is the Python code that I'm currently using for this. It's called statmorph. It's really, really good for this. As you see, it assumes that this galaxy is part of the system, and it gives us really bad numbers. For instance, let's say the asymmetry goes up to 0.2. That's quite high for something this regular. So when we instead use the clean image, the asymmetry is 10 times lower, at least. There are slight differences due to other things, but yeah, it goes to 0.04, which is much more reasonable considering the shape of the galaxy. So cleaning is key. So the whole process that this galaxy, the image is going through, you only need to feed the IDE, the coordinates, and the redshift of the galaxy. And the program that I wrote, which as of now is called Morphology Streamline, to be defined, does everything, including fetching the image and files and everything that's necessary until you get the morphologic metrics. These metrics then are used as the input for the machine learning classifier, which we're trying several techniques. Currently, random forest seems to be the best. And finally, you have a classification for all galaxies at different stages. So this is just to quickly show how the 3 most important tools for cleaning the image work. So first you have artifact detecting and cleaning. As you see, the artifact has been removed. In this case, this artifact is not really compromising the image, but just to show what the program does. Then another important thing is to remove stars because they are not part of the galaxy, so they should not be measured. So here we detect a star that's considered to be within the body, the segment of the galaxy, and the blue ones would be on the edge. And the red ones are just outside. We don't really care about those. And so you have the raw image and the clean image after removing the stars that are indicated here. And finally, the blending, which is the thing I showed at the beginning, where, as you can see, there are 3 objects here identified, one of which should stay because we cannot tell for sure that it belongs or not to the same plane. But the other thing is certainly something else. It is a star, so it has been removed because the star removal part does not always work 100% fine. It depends on what other surveys have defined as a star. So this is an added step that's really convenient for this. There are other minor tools included in this code, which are, well, all the ones you see here, not really important, but they do help to improve the segmentation and detection in the image. And this is dark for some reason. Yeah, I don't know what happened here, sorry. But well, finally, we have the current results for all stages as they have been classified by these different methods. As you see, the accuracy numbers are not as nice as we would like, but what has been clearly observed now is that increasing the data does a long way for improving these numbers. So right now, I am in the process of increasing the data to improve the classifiers. And let's say by a rough approximation, I believe that we are going to have an accuracy of 0.8 or 80% roughly. So this is the current stage that the work is on. Thank you.
Alejandro, other questions, please?
How different times project you can actually do the great and 2 years.
So that was the original idea, but Galaxy Zoo only considers if something is or not a merger. It doesn't really care about stages. So I know we discarded that. Yeah.
I didn't know it was had enough information there.
But, yeah. And also in Galaxy Zoo, you can trust most of what they observed, but when it comes to mergers specifically, the public cannot be trusted as much as I wish, because we tried and there are some things that are really mistaken.
Is there one question more, maybe? No? Okay, then the next speaker will be Pablo.
Hello, my name is Pablo. I started my third year of the PhD last week, and my supervisor is Carlos Oporta, and this is the provisional title of my thesis, testing the black hole non-pair conjecture with extreme mass reaction spirals. So we work with LISA. LISA, as some of you may know, it's an international collaboration between LISA and NASA. It will consist of 3 identical spacecraft that will exchange laser beams across 2.5 million kilometers in space. This first space-based interferometer will unlock the millihertz gravitational wave band, something that cannot be achieved with ground-based detectors like LIGO or Virgo. And the launch is expected, hopefully, in 10 years, in 2035. So, among all the different sources LISA will be able to see for the first time, I'm interested in extreme mass reaction spirals. These are basically compact objects, typically a stellar mass black hole or neutron star, that gets captured by a supermassive black hole in the center of galaxies. And these compact objects travel very, very fast at very relativistic speeds and very close to the zen horizon. So they create like many cycles in the last year of each spiral, specifically 10 to the 5 cycles during 1 year. And the detection rates depend on the astrophysical model you use to do the estimates, but we will be able to see either 1 embryo or a few hundred. There is a big uncertainty. And the main point is that these systems are great laboratories to test general relativity to the fundamental level. So I'm working in the fundamental physics group, LISA. The main aim is to explore the nature of gravity and black holes. And in my work, what I do is to study the multipolar structure of these black holes in the center of galaxies. To answer the question of whether these objects that we know they exist in the center of galaxies are Kerr black holes, so rotating black holes, as predicted by general relativity, or some other more exotic compact objects we don't know. And as I said, embryos are great to do this because you can imagine them as being sort of microscopes that actually probe even the tiniest features of the spacetime in the very, very vicinity of the massive body. And so I mentioned this multipolar structure. I will briefly outline what are these multiple moments that some of you may know from Newtonian physics. You can have your potential expanded in terms of these scalar quantities, this MLM. This basically gives you information on the gravity field of your object. A few years ago, ESA as well launched a satellite called GOTSE. This was to map with unprecedented detail the Earth's gravity field. Here you can see a picture of how complex the shape of the Earth is. They managed to measure up to 200 multiple moments. This gives you an idea on the complexity of the shape. So if you have a spherical object, the preferred spherical object, you only have one multiple, which is the monopole, which is basically the total mass of the object. If you break the axial symmetry, then you have your multipolar structure gets a bit restricted, because then it means that all the multiples within different from zero values. And if you add another symmetry, so the object is symmetric with respect to the equatorial plane, then you get even more restricted multipolar expansion, and all the multiple moments with a lot vanish. So black holes are much less scary, complex than the Earth in shape, because they are very, very spherical. And you only need two multiple moments to define them, the mass and the spin. And this follows the famous Noether theorem, which basically says that the only information you can extract from a black hole, is the mass and the spin. And if you want to derive all the rest of the infinite amount of multiple moments, you can just put them in this formula, which is the mathematical expression of the Noether theorem, and derive. So what you can do ourselves with these gravitational wave signals we will be able to see is to extract the quadruple moment, which is the first multiple moment beyond the mass and the spin, and compare the value to the Kerr black hole value from what general relativity predicts. And if it doesn't match, then it means we are observing an exotic object that we don't know. So this is enough to verify or disprove that the object is a Kerr black hole. But if you want to pinpoint the identity of the object, you need to go to higher orders. And that's what we did. So we added the first multiple moments to break these two symmetries of the Kerr metric. And we use one single embryo observation to see how well ICE-CSIC will detect this breaking of the symmetries. And we see that this is quite accurate, far better than any other telescope. So this type of test of GR, like Event Horizon Telescope, for example, because you can reach the 10⁻³ accuracy. And so you may think, okay, but what kind of objects that we don't know break these two fundamental symmetries that we believe describe most of black holes in the universe? Actually, we have a deep search in the literature. We have found that in other theories beyond GR, like string theory, you have these foosballs, which are like the substitute of black holes, and they actually do include in the geometry the breaking of these two symmetries. So we know string theory, for example, is a theory of quantum gravity that is very difficult to test, because you need like accelerators of the size of the solar system. But if you look at what string theory predicts for the most extreme energetic objects in the universe, you can put some constraints on it using LISA with embrace. And this is some constraints that we did to show how well embrace can, so how well can we extract the information of the object with one single embrace observation. For example, the mass, you can know the mass with an error in 10⁵, and the spin as well, 10⁴. This 10⁻³ is to extract the quadruple and compare it to the Kerr black hole and see whether it is not a Kerr black hole. And these other components, they break the symmetries that I mentioned. And the most important thing is that LISA will be able to scan or map any deformation on the surface of the object to the 10⁻³, and even locate this deformation on the surface of the body to 10⁻³. So now that I have hopefully convinced you on the potential that LISA has to do this sort of test of GR, we now want to work towards more realistic models. And the first step is to work to compute the modified frequencies of a point mass orbiting what we believe, orbiting a Kerr black hole. Because you cannot change the geodesics, which is something that Carlos in his talk last week introduced. These geodesics are trajectories in full spacetime. You have to leave them as they are. What you can do only is to modify the frequencies. So that's what we did. Here you have the frequencies according to Kerr black hole, and these are the shift due to some beyond GR effect. In this case, is the deviation in the quadruple, which I mentioned is the first example to break this degeneration. And so if you compute the final modified frequencies, you see that it's almost pretty similar to the Kerr one, to the GR ones, but it changes to some decimal parts. And actually, this is quite useful because an embryo, I said in the beginning that an embryo does 10⁵ cycles in 1 year of spiral. So if you have a shift of 10⁻⁵, actually the cumulative dephase of this motion gives you the order of 1 value, which is very good for waveforms because we study the overlap between GR and non-GR. So this is the first step to work towards this modified embrace. So as a conclusion, I hope I giving you an idea on how well we'll be able to test this GR with LISA. And as I said, the future work and also ongoing work that we have here in the Institute is to work towards more realistic models that put to the test general relativity. Yeah, that's it. Thank you very much.
Any questions?
I understood correctly, you're assuming that black holes are very spherical.
Well, they are like a bit, scale black holes are a bit oblate because they rotate. So they are like a bit squished. And that's how the quadrilateral defines the formation. It's not spherical, it's like a bit of a ellipse, but it's very tiny. So it's almost spherical.
How do they are so spherical?
Black holes?
Yeah, it means something theoretical.
Yeah, I mean, well, this is a very like fundamental question, like why black holes are so spherical. I guess, yeah, I don't know.
And then so spherical if the spin is high.
If the spin is very high, it deforms.
Yeah,
It's a reversible black hole that has no rotation is complete spin. It's very, very simple.
This is part of the parameters of the model. So your multiple moments contain the degree of
Yeah, the degree
Exactly,
of deformability. So the spherical object is a monopole of only one multiple moments mass.
Does that comment if it's very nice? In principle, let's say that you don't know what neutrons are made of, and you just compute them mathematically, they would be very good, for example, the same. But then there are other forces there due to the fact that we know which kind of material is there and makes them not spherical and spherical. So maybe this is just because we actually don't know what is it.
no, that means that the multiple moments characterize uniquely the object. So neutron star cannot have the multiple moments as a black hole. And you cannot have neutron star of 10 to the 6 solar masses. So, what you were saying. But actually the small one, we haven't done this, but the small one can be a neutron star. And we can add also the multiple moments of the small one. And then there is this idea of the tidal deformability that is now falling like but this is just one parameter. It's very intricate how we can perform.
Okay. And thank you so much, Pedro.
Okay. So this is Pedro, and today I'm going to be presenting work that I've been recently doing, which is basically estimation of the standard fundamental parameters using the small g and spectroscopy. So recently, a group from the University of Sydney has presented a homogeneous catalog of oscillating solar-like stars by reanalyzing the individual frequencies of 765 main sequence and subgiant branch stars. So they presented a catalog including nu max and delta nu. So this nu max is basically the maximum frequency at maximum power, and is proportional to the surface gravity of the star and the effective temperature. And delta nu is the spacing between two overtones, and is proportional to the mean density of the star and the effective temperature. So with this catalog, what we did is that we completed the catalog because we saw some missing data. We complemented observations with spectroscopy. We calculated the impact of the chemical composition, and we estimated fundamental parameters and compared with previous results. So, okay, if we took a closer look at the catalog, we see some missing data, for example, for nu max, for delta nu, and some errors. So what we did is that we completed the catalog using a linear fit. And in log space, nu max and delta nu are really well correlated. So what we did is that we used this linear relation, and we also added a term which takes into account the dispersion of the 50 closest stars, just to have more accuracy in the results. So with the catalog completed, we complemented the catalog with spectroscopic data using effective temperatures and metallicities from 3 different sources. And also, we added the chemical composition of the alpha elements, which are oxygen, magnesium, silicon, sulfur, calcium, and titanium. So then we computed the best fit alpha enhancement ratio. So let me explain a bit about this best fit alpha enhancement ratio. So basically, the alpha enhancement ratio is a ratio that takes the overall enhancement or depletion, taking into account all the alpha elements. But we don't trust that spectroscopic alpha enhancement ratio. And I came with the idea that we have to imagine a solar-like star that has an enhancement in the oxygen abundance, and another solar-like star that has an enhancement in magnesium, and a third star that has an enhancement in oxygen and magnesium. So if we want to reproduce the stellar evolutionary track of that star, we could simply add the evolutionary tracks of the star with oxygen and magnesium enhancement. So with that idea, what we did is that we computed a grid of stellar evolutionary models from the main sequence, the red giant branch, from different masses, different metallicities, with the particularity that all these models have individual alterations in the abundances of the alpha elements between minus 0.6 to 0.6. And we discovered that along each evolutionary point of the track, all the differences in the alpha elements follow a quadratic trend. So what we did is that we computed a grid of A and B parameters, so we could reproduce any stellar track with any chemical composition using this equation in here. We could do the same using the alpha enhancement ratio, but I said that we don't trust the spectroscopic alpha enhancement ratio. So what we did is that we subtracted these 2 quantities here and we minimize it. If we minimize this quantity, we obtain the best fit alpha enhancement ratio, which takes into account the chemical composition and also the evolutionary stage of each star. So with that, we computed the best alpha enhancement ratio for the stars included in the catalog. And then with that computed, we came to compute the estimation of these masses, radius, surface gravity, and ages. We could use the scaling relations, but if we want more accuracy, we will have to use some pipelines that use Bayesian inference. And these pipelines have a lot of stellar models, a grid of stellar models for different masses, different metallicities, which are calculated with these features. I'm not going to enter into detail. But then for approximate Bayesian inference, what we use is that each variable is assumed as a random variable, which is proportional to a prior knowledge times a likelihood. This likelihood has an Gaussian-like form, and the prior knowledge is proportional for mass to this initial mass function, and in h is proportional to 1 over the maximum h. So then, taking the seismic variables, nu max and delta nu, and the spectroscopic variables, effective temperature, and metallicity, which is corrected by the best alpha enhancement ratio, we computed stellar masses, radius, fundamental parameters for these stars included in this catalog. So here we have the stars in the HR diagram, here in the keel, and here we have stellar mass over stellar radius. So then we compared the results with previous works, which is the first APOCAS, and we see that, for example, for seismic observations, we don't have any big differences, but when we go to spectroscopic parameters, we have some differences in the effective temperatures and metallicity. And that's why, that's because in the first APOCAS, they used different effective temperatures and different metallicities than the ones that we are using. So this also implies that we will have huge differences in masses, radii, surface gravity, and ages, which are mainly due to differences in the metallicity and in the effective temperature. So yeah, I'll leave you with the conclusions, and thank you.
Any questions? No questions? Please.
But kind of really more very basic question, but one sentence, what is the goal of your research? What is the open question trying to answer
The impact of chemical composition
on
on the estimation of these parameters.
so even more like basic, even like
So the,
sure, like what is the science?
the science that I'm trying to explain is that
What is the question with it?
Yeah.
What
is that normally we don't use chemical composition, or we don't trust chemical composition in stellar evolutionary models. And my idea is to bring to the table that chemical composition plays a key role in stellar evolution, because we see here that these tracks have the same mass, same metallicity, but look, for example, if you enhance oxygen, here appears a convective nucleus. So if you take into account chemical composition, big changes happen in stellar evolutionary models. So that's like the point of assuming chemical composition in stellar evolution.
Or not. Okay. Okay. Thank you. Then Victor, our last speaker.
It doesn't look good. Hi, I'm Victor Rodriguez Morales. I have just started my third year as a PhD student at the Destination of Baronespa. My PhD is about AGN outflows and feedback in dark galaxies, and during the last year, I've been focused mainly in the DESI first data release. So let's start with an introduction. AGN outflows, what are they? AGN released energy in form of radiation, winds, or in form of mechanical radioplasma jets, and these winds and jets, when interacting with the interstellar medium, is what we call outflow. They are typically found in massive galaxies, and they are an essential ingredient to understand the evolution of galaxies. In massive galaxies, AGN feedback is generally believed to prevent gas from cooling and to redistribute it, thus suppressing star formation. And galaxies are assumed to be regulated, the star formation in that galaxy is assumed to be regulated by stellar winds coming from supernova, but things have recently started to change. We have observation and simulation providing several evidence of AGN outflows in feedback in dwarf galaxies. So we are talking about AGN outflows, so we need to know how can we identify AGN. We use VPT, emission light diagnostic diagrams, where we can compare the emission light radius N2 over H alpha, H2 over H alpha against the oxygen 3 over H beta. And we can classify this emission light radius in this diagram, and they told us the ionization source of the galaxy. If it falls in this region, it's AGN. This is the star forming, and this region in between, it will be composite. If we combine the N2 and S2 VPT, this classification became wider. We have AGN liner, star forming AGN. And also we need to know how can we identify outflows. My work is very much is based in the optical regime. So in the optical, the oxygen 3 is the typical line we use to identify outflows. If the oxygen 3 emission line needs to be properly fitted a broad component in addition to the narrow component. This broad component indicates that there is an extra kinematic component different from the typical circular motions of the galaxy. This is an indicative of outflow signatures. So let's explain a little bit our sample. As I said before, our sample is drawn from the CDR1, selecting those galaxies addressed below 0.45. And this galaxy were the spectrum of this galaxy were fitting using the MFIT code that is described in Puchator 2024. We find almost 60,000 galaxies with AGN outflow signatures. galaxies in general. No distinction between dwarf, AGN, non-AGN, massive. Then we apply different cuts. The cut in mass, where the sample dropped to 25,000 dwarf galaxy without flow signatures. We remove the double peak sources because double peak sources in the oxygen-free emission line can be explained by outflows, but also by merger or dual nuclei in the galaxy. So we don't want to contaminate the sample. So we exclude the double peak sources. And then we classify with the BPT diagrams, the subsample over here, ending with 1500 AGN dwarf galaxy without flow signal. We have computed the kinetic and energetic properties of the outflow. The WAT velocity is the typical outflow velocity estimator. It's defined as the width containing the 80% of the flux. And we have also, I don't know to go into the equations. We have also computed the outflow mass, the outflow radius, the kinetic, and other energetic properties as the kinetic energy rate and the mass rate. We have said, and this is important, that we have 1500 AGN dwarf galaxy with outflow signatures. But this doesn't mean that the outflows are coming from the AGN. We need to investigate the driving mechanism behind these outflows. To this purpose, we have studied different oxygen-free properties from 4 different samples of dwarf, massive, AGN, and non-AGN galaxies, and comparing the velocity dispersion, the difference in the velocity dispersion between the narrow and the broad component, and the velocity shift between this narrow and broad component. In the cumulative distribution function in the KS matrix, we can see that for the sample of AGN galaxies, massive and dwarf, the distribution is similar and different from that of the non-AGN massive and dwarf galaxy with outflow signatures. What does this mean? The AGN cannot be the driven mechanism behind the non-AGN galaxies because we don't have an AGN in this galaxy. So the driven mechanism should be different between the non-AGN and the AGN galaxies. This is become clearer when we compare the WAT velocity distribution of these 4 samples of AGN, non-AGN, dwarf, and massive galaxies. And when comparing, well, we can see here that the higher outflow velocity that the AGN galaxies have a tail towards the higher outflow velocity. And when comparing the outflow velocity against the oxygen-free luminosity, we see clear two distribution for the non-AGN dwarf galaxy and the AGN dwarf galaxy. So we have applied a perimetric cut in the outflow velocity, WAT equal to 250 kilometers per second, to distinguish between the origin of the outflow. So those AGN dwarf galaxies with outflow signature with velocity higher than 250 kilometers per second are classified as AGN outflow. These outflows have an AGN, are driven by an AGN. So the sample drawn from 1500 AGN dwarf galaxies with outflow signatures to 1200 dwarf galaxies with AGN outflows. And this is the biggest sample to date of dwarf galaxy with AGN outflows. We have made some scaling relation comparing energetic properties against the volumetric luminosity of the galaxy, and we see a linear trend through all the mass regime, indicating that AGN outflows in dwarf galaxy behave similarly to those in massive galaxy. Also, we have computed the escape velocity of the dark needed to escape the dark matter halo of the galaxy using abundance matching and assuming an spherical narrow and wide profile. There are different free parameters, so we have to do this analysis for 8 different models, and in all the models we have the same results. That is, the AGN outflows in dwarf galaxy are more capable to escape the dark matter halo than those AGN outflows in massive galaxies. These implications are interesting because we are removing gas from the center of the galaxy to the outer part of the galaxy, and that may hit the interstellar medium and thus suppressing the star formation. Furthermore, eventually this outflowing gas will escape the dark matter halo and create the circumgalactic medium, so it will not be recycled again in the galaxy. So for those dwarf galaxies able to escape the dark matter halo, we expect a star formation suppression. Okay. The conclusions, well, here I leave the conclusion, the detection of the biggest sample to date of dark galaxy with aging outflow. We find a pioneering depth hole in the outflow velocity to distinguish between the stellar, between the origin, the stellar origin or an aging origin. We study the kinematic and energetic properties of the outflow, and we find that the aging outflows in dark galaxy are more capable to escape the gravitational potential produced by the dark matter halo than those in massive galaxies. And that will be it. Thank you.
Any questions?
Have you also observed if there's a relation between the presence of outflows and say the star formation rate to see how it is affecting the?
Yes, I should have backup plots. I have compared like the kinetic energy rate of the outflows against the star formation rate. The star formation rate was derived by two different modes, H alpha, but H alpha have agent contributions, so we also use acidic fitting. The acidic fitting, and we see that for this, and we compare to the star formation rate expected if the supernova drove this outflow. And we see that for those galaxies under 250 kilometers per second are below the expected energy of the supernova, and those with higher, but the higher fraction of those with higher velocity than 250 kilometers per second are above this expected relation with supernovas, meaning that the supernova is not energetically enough to justify these outflows. This is another argument in the direction of this velocity cut in WH velocity is a accurate cut, accurate version distance of the origin.
Please.
I'm not able to listen.
Is it right?
Below 0.45. 0.45 is the relative range. With difference between the we haven't done yet evolution with redshift with the outflow properties. We are thinking to do it when the data with DC data at redshift higher than 0.45 and compare also to AGN detected in the literature at higher redshift to see if we can explore some kind of cosmological evolution of the outflows with the redshift. But we haven't done that yet. This is work in progress. Yeah.
Okay, more questions?
Okay.
Thanks. And then really thank all the 5 students. They are the bravest one. Actually, I asked many times. So thanks so much for listening. This was unfortunately a completely male PhD. I just realized. Maybe we change that for the next one. It will be in April 12th. Okay, maybe this time wait for me with the pizzas. Yeah.